let's look at some neutralization reactions. Again, I think this is something that would have been a little bit better to cover in the chapter on acids and bases, and just in case, we're going to review a little bit. So a neutralization reaction occurs when an acid and a base react. So if I got an acid and a base, I'm going to end up with a salt and water. So remember, an acid is a proton donor, a base is a proton acceptor. So here is our stereotypical go-to reaction, right? I've got my go-to strong acid, HCl. I've got my go-to strong base, and they're going to form my go-to ionic compound, sodium chloride, right? Because I've got the conjugate base of the strong acid and the conjugate acid of the strong base, sorry, and NaCl and H2O. In general, an acid and a base are going to react to form a salt, and that's any ionic compound whose cation comes from a base, and any anion who comes whose anion comes from an acid. These are all proton transfer reactions. Remember, not all salts are neutral, right? They can shift the pH if they're the conjugate of a weak acid or a weak base. So, for example, if I had ammonium nitrate, that would shift the pH and it would be acidic. Right? If I had something like sodium acetate, that would be weakly basic. If I had something like ammonium acetate that's got the conjugate of a weak acid and the conjugate of a weak base, I'd have to look and see, does the Ka of the acidic part, is it larger than the Kb of the basic part? So, for example, as an example problem, what volume of 6 molar sulfuric acid is needed to react completely with 37 grams of sodium hydroxide? Right? Products would be sodium sulfate and water. Right? These acid-base reactions are going, like precipitation reactions, are going to be exchange reactions where we've got AX plus BY goes to AY and BX. Right? Where our BX is usually going to just be plain old ordinary water, and AY is going to be the salt. So, for example, predict the following products and write the balanced chemical equation. So hydrochloric acid and sodium hydroxide, HCl plus NaOH, those will completely dissociate into their component ions, will form Na plus and Cl minus and HOH, so NaCl and water. Nitric acid, strong acid, and ammonium hydroxide, and it's going to be a strong base. HNO3 and NH4OH going to dissociate, and they're going to drop and swap, and they'll form, not drop and swap, they'll exchange and form nitrate. That's the leftover part of this nitric acid. Ammonium from the ammonium hydroxide, and water. Sulfuric acid and sodium hydroxide, H2SO4, and NaOH will give me Na plus and HSO4 minus and water. Right? And so those have all been strong acid, strong base types, right? And you're going to assume complete dissociation of both the strong acid and of the strong base. So I'll have H plus and OH minus to give me H2O, right? And the other guys over here, right? Remember, these guys are going to be spectator ions. Right? Either one of these you could use. You could either do H3O plus and OH minus, giving you two H2Os. At neutralization, when you've got equal moles of the strong acid and equal moles of the strong base, and you mix them together, the pH will be 7. Right? If there is any excess of the acid, it will be acidic. If there's any excess base, the solution will remain basic. Right? What if I mixed a weak acid and a strong base together? So something like acetic acid over here and sodium hydroxide. Well, I'm still going to form water, but now I've got sodium acetate as the other part. Right? We're going to assume that this guy completely dissociates. Right? So we're going to react our acetic acid and hydroxide to give us water and acetate, right? Because all of my group 1 cation containing salts are going to be soluble. Right? So the sodium is going to be a spectator ion. This guy is not a spectator ion because it came from here. And so after neutralization, I've got water and this weak base in solution. I've neutralized my weak acid with the strong base. I've got weak acid left over. And after neutralization, my pH is going to be bigger than 7. I could take a strong acid and react it with a weak base. And so HCl is a strong acid and ammonia is a weak base. And I'm going to form ammonium chloride. Ammonium chloride is soluble. The chloride doesn't have any substantial acid-base properties, but the solution is going to be acidic because of the ammonia part. So we assume it completely dissociates. The NH3 stays as NH3, and the HCl splits up into Cl minus and H plus. The H plus jumps onto this NH3 to give me NH4 plus. If I wanted to do it with the full-on having the H3O plus, this would be the net ionic equation. After neutralization, I'm left with water, and the water is a spectator, and NH4 plus. Right? NH4 plus is weakly acidic, right? And so it's going to go with a pH below 7. What if I took a weak acid and reacted it with a weak base? Well, that's a little bit trickier. So here I've got something like acetic acid and I've got ammonia. Right? Well, my product is going to be ammonium acetate, right? Where my weak acid and my weak base will react to form NH4 plus, which is the conjugate of the weak base, and then it's going to form acetate, which is the conjugate of the weak acid. Which one is it going to be acidic? Is it going to be neutral? Well, that's going to depend on whether the Ka for the acidic part is bigger than the Kb for the basic part. Right? If the acetate base part has a bigger Kb than the Ka for the ammonium, and then it's going to be basic. Right? So you're going to check the Ka versus Kb. So when we're doing this sort of neutralization, we're talking about having the number of moles of the acid and the number of moles of the base be equal to each other, right? So we had equal number of moles of this and 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 this and equal number of moles in this and this. We will see what happens when you don't have equal number of moles in a second, but the idea is that you want to figure out how to determine the equivalence first, right? So that's the equal number of moles situation. So in order to do that, you need to use a mole method strategy. So convert the experimental quantity that you're given into moles, and you're either going to do that using molar mass, grams per mole, or molarity, so concentration and a volume. Right? Then you're going to use the stoichiometric coefficients or the mole ratios to convert between the substances. So you need a balanced chemical equation. And a lot of the time, but not all of the time, it's going to be 1-to-1. What if you got something like strontium hydroxide? Well, strontium hydroxide is going to be a base. It's a strong base, but it generates 2 hydroxide ions per mole of strontium hydroxide. So you've got to check the stoichiometry, right? So don't forget this step. Convert to moles to the desired experimental quantity using either molar mass or solubility. So you can go from mass into moles, or you can go from volume and concentration into moles. All right, so here's another little flow chart. So I can get grams of A, and use the molar mass of A to figure out moles of substance A, or I could use the concentration and the volume and figure out the molarity, or I could go from the molarity and a volume into moles of B, or moles of A, and I could do the same thing down here with the substance B. That would be like our base, right? Acid, B for base. So I could figure out the grams of the base, use the molar mass to figure out moles of base, or I could use a volume and a concentration, and then I've got to use the stoichiometric ratio between the two. Right. So at our equivalence point, the acid has been completely reacted with the base. So that's when our moles of acid are going to be equal to the moles of base added. And so the moles of, like we did a strong acid HCl reacting with a strong base NaOH. And that's when those are equal to each other. But it could be, the moles of the weak acid, right? Acetic acid reacting with the moles of potassium hydroxide. Right? You want to be a little bit careful with this because when we're going to do titrations, have a case where the moles of the conjugate weak acid and the conjugate weak base are going to be equal to each other. So make sure in your head you've got it clear as to whether you're doing neutralization and equivalence, where the moles of the two added things are equal, versus the halfway to it when the moles of the conjugates are equal to each other. So how do we visualize this equivalence point? We're going to use an indicator. One of the most popular ones is phenolphthalein. That's an organic dye, and its color is going to depend on the solution's acidity. So an acidic solution, where it's going to be less than 7, it's going to be colorless. Near 7, it's going to be a very pale pink, and near, in a basic solution, it's going to be a nice bright fuchsia pink. Right. So let's do an example here. What volume in milliliters of 6 molar hydrochloric acid is needed to react completely with 37 grams of sodium hydroxide? The products of the reaction are sodium chloride and water. So I've got 1 HCl and 1 NaOH goes to NaCl and H2O. The molarity of the solution is going to be used as a conversion factor in a stoichiometry problem. So 6 molar HCl really means 6 moles of HCl per liter of solution. So that means in 1 liter of solution, I've got roughly 6 moles. I'm going to convert the grams of sodium hydroxide into moles of sodium hydroxide. So 37 grams of sodium hydroxide divided by the molar mass of 39.9 grams. Now there's a 1-to-1 stoichiometry, so I need 0.92 moles of HCl. If 0.92 moles of HCl, if I've got a concentration of 6 moles per liter, moles cancel each other out. I need to convert that into milliliters. 150 milliliters of 6 molar HCl are needed. Right. But let's do some other situations. What if I've got 100 milliliters of 0.1 molar NaOH and I add too much HCl? So adding in 150 milliliters of 0.1 molar HCl. So you got 150.15 liters of HCl times 0.1 mole per liter is 0.015 moles of HCl. And then I just do a difference here. So 0.015 moles of HCl minus 0.01 moles of sodium hydroxide leaves me left over 0.005 moles of HCl. Right? My pH, I got to convert this into molarity, is going to be 2.3. And these are just limiting reactant problems. Right? So let's say I've got too little HCl. Right, same setup as before, but I've got 0.005 moles of HCl. I subtract the moles of HCl from the moles of sodium hydroxide because I've got more sodium hydroxide than I do HCl, which means I got 0.005 moles of NaOH left over. I take the base 10 log of the concentration to give me the pOH, which is 2.3, which means my pH is 14 minus 2.3, or 11.7. Right, so I'm just going to use the excess OH or H plus to find the pH. And don't forget to adjust for the new volume. So if you took two things and you added them together, right, you've got to adjust for that volume. Right? What if I've got a strong acid and a weak base, or a strong base and a weak acid? Right? The last situation was I've got a strong acid and a strong base. What if it's a strong and a weak pair? Well, I could either have equal moles of strong base. Right? So it's a conjugate weak base in solution. You treat it just like you would using a weak base problem using Kb. Don't forget to correct for the new volume. I could have excess moles of the strong base added. Well, if I've got excess moles of strong base, I've gone past my neutralization point. I just have OH, extra OH minuses. Right? I still have some of my conjugate weak base in there, but I've got extra OH minuses. I'm just going to find the concentration of OH minus in the new volume and find pH like you would for a standard strong base problem. Right? And the opposite will happen if I've got a weak base, right? So if I've got a weak base and I start off with a weak base and I don't add enough, right, if I've also got equal moles of strong acid and strong base, it becomes a weak acid problem. If I've got excess moles of the strong acid, it's a strong acid problem. If it's not enough, right, I've got a conjugate weak acid and a conjugate weak base in solution, then it's going to become a buffer, right? Then it's like that common ion problem where I'll have both the acid form, and the base form in solution. And we give this a special name if I've got significant amounts. It's called a